Good morning, everyone. My name is Ting from Huazhong University of Science and Technology. It's a great pleasure to present my work here. My talk today is about GearDB, a GC-free KV store on HM-SMR drives with gear compaction. I will give this talk in 4 parts. First, let's see the backgrounds and motivations. In the background part, I will answer, why do we run KV stores on SMR drives? As is well known, SMR drive is a promising technology driving the disk array density increases. It achieves high capacity with overlapping checks like shingles on a roof, just as shown in this figure. Checks are grouped by zones, and SMR provide free read with small read head, but its write head covers several checks, so random write risks damage valid data on overlapped checks. That's why sequential write is preferred, and the log-structured write is a common practice to do the sequential write. SMR drive can basically be divided into 3 parts, that is, drive manage, host aware, and host manage. In our study, we focus on HM-SMR drive, the host managed SMR drive, because it not only has the property of large capacity, low TCO, but overmatches the other 2 types with predictable performance. HM-SMR drive are already produced by drive vendors such as Seagate and Western Digital, and our test drive in this study is the 13 terabyte HM-SMR drive from Seagate. So HM-SMR drive is an ideal choice for the applications that write data sequentially, read data randomly, and demand predictable performance, and need control of how data is handled. Those applications are common in domains such as social media, cloud storage, and life science. LSM-tree-based KV stores are widely deployed in write-intensive scenarios. Popular KV stores like LevelDB, Cassandra, HBase, RocksDB are built based on LSM-trees. It has high write throughput by batching write in memory and thus provide sequential write in individual files. LSM-tree has faster read and faster range queries. As mentioned by our keynote speaker yesterday, non-SQL KV store concerns predictable performance, and with the explosively growth of data volume, KV store also demand increasing large capacity. After the basic understanding of LSM-tree-based KV stores and HM-SMR drives, here we summarize their benefits for each other. First, LSM-tree-based KV store batched sequential write that is very good for hard disk drives, while HM-SMR drive requires sequential write. LSM-tree-based KV store demand large capacity and concerns predictable performance, while HM-SMR drive can provide large capacity and predictable performance with low TCO. So, there is a feasibility to building KV store on HM-SMR drives. In industry, there are already some attempts, such as SMR from NetApp and SMR-based KV store from Huawei. However, key value stored on HM-SMR drives still have its challenge. The main problem is redundant cleaning processes in both application level and the storage level. When you run an LSM-tree-based KV store on HM-SMR drives, data will sequentially write to HM-SMR drives in this way. So we can see SS tables from different levels that have different compaction frequency are mixed in the same zone. In the application level, LSM-tree requires compaction to keep tree balance. For example, suppose we want to compact an SS table from level 1 to level 2. We first will fetch the victim SS table in level 1 and the overlapped SS table in level 2 into memory. Then we merge and sort them. Finally, we write them back to level 2. During these compaction processes, invalid data invalid KV items are cleaned. However, it produces stale SS tables and thus leaves holes on disk, making the disk space fragmented and requiring garbage collection. So that is what we say redundant cleaning processes. What we want to do is eliminate the garbage collection on HM-SMR drives and improve the compaction efficiency. To demonstrate the drawback of redundant cleaning processes, we will do some motivational tests. We're running LevelDB on an HM-SMR drive with 2 garbage collection policies. The first one is LevelDB greedy, which reclaims zone that has most invalid data. And the second one is LevelDB cost-benefit that reclaims the zone has the oldest data and the lowest space utilization. Garbage collection are triggered when free space is under 20%, and zones are reclaimed by moving valid data from a victim zone to another zone. The test is randomly loading an 18 GB data set to restricted disk space. We make the valid data takes 80% of the disk space. So here we record the valid data volume and the time consumption of garbage collections in every 10 minutes. Let's see this. The 2 points show that more than 15% of the execution time is spent on garbage collection when valid data volume is 17% of the disk space. So garbage collection takes a substantial proportion of the execution time that will definitely degrade system performance. Here we show the space utilization of LevelDB cost-benefit and LevelDB greedy. This figure is the CDF of zone space utilization. Zone space utilization is defined by the ratio of valid data volume in this zone and to the zone size. From this figure, we can find 85% of zones have a zone space utilization that ranging from 45% to 80%, which means most of the zone are mixed with valid data and invalid data. It brings poor overall disk space utilization, that is 16%. Of course, we can improve the space utilization if we conduct garbage collections more frequently, just by changing the threshold of garbage collection. However, here comes the test result is that system performance decreases with the disk space utilization in this way. So here, I will summarize our motivational test. First, garbage collection brings large overhead. Second, KV store on HM-SMR drives show poor space utilization. And third, system performance decreases with disk space utilization. These 3 facts motivate us to build GearDB. A KV store on HM-SMR drives aims to achieve high performance and space efficiency. Next, we will see GearDB's design. GearDB has 3 new techniques, that is, new disk data layout, compaction window, and a novel gear compaction algorithm. The key idea of the data layout is that each zone one zone only serves SS tables from one level, so that each zone in an LSM-tree has multiple zones according to its data volume. For example, in this figure, level 2 has 2 zones and level 3 has 6 zones. Since SS tables in a zone comes from the same level, they will share the same age and the same compaction frequency. So that's potentially resulting in less fragmented disk space. Okay, based on the disk data layout, we will introduce compaction window. A group of zones are selected rotationally to construct a compaction window for every level. For example, those emphasized zones are picked as the compaction window of their level. Let us put it in another way. Each level has a compaction window, and a compaction window is composed of a group of zones belonging to that level. By default, the compaction window size is 1/4 of the size limitation of level I. Compaction window is used to restrict compaction and fragments. Now we come to our gear compaction. Gear compaction aims to automatically clean compaction windows by conducting compaction only within compaction windows. Next, we will detail gear compaction algorithm in this figure. But we first need to note that for a clear description, here we only show SS tables in each level's compaction window. Okay, here comes gear compaction. First, gear compaction starts from level 0 and level 1. First, victim SS tables in level 0 and overlapped SS tables in level 1 are fetched into memory, merge and sort, just as a conventional compaction do. But the big difference is that the resultant data in memory will be divided into 3 parts. That's out of compaction window of level I, in compaction window of level I, and out of level I. So, the first part, out compaction window level I, is a part of data that overlapped with some SS tables that are out of level I's compaction window. For this part of data, we just write it back to level 1. So our step 2 is write back the out compaction window level 2 back to the level 1. The second part of data is out level I, which means data does not overlap any SS table in level I. So here, in this example, is that data does not overlap any SS table in level 2. For this part of data, we just dump it to level 2. Because this dump operation, we reduce the further compactions. And in compaction window level I, this part of data means data overlapped with some SS tables in level I's compaction window. So we compact this part of data with the overlapped SS tables in level 2's compaction window in this way. The resultant data will be further divided into 3 parts according to their key range, that is, out compaction window of level 3, in compaction window of level 3, and out level 3. Correspondingly, they will write back to level 2 and dump to level 3 and do the further compaction. So we can see that gear compaction proceeds recursively in compaction windows level by level. So it will stop when compaction reaches the highest level or the resultant data does not overlap the compaction window of the next level. From the above introduction, we know GearDB only proceeds within compaction windows. Thus, invalid data are restricted within compaction windows. Since a zone full of invalid data can be reused as empty zones, gear compaction reclaims zone automatically. The reclaim of compaction windows works in a gear fashion. As shown in this figure, if we compare a gear as a level, then a sector represents a compaction window. A single move of a gear represents we automatically reclaim zones in a compaction window by compaction. And a full round move of a gear represents reclaiming all the zones by compaction. In GearDB, reclaiming all compaction window in level I results in cleaning one compaction window in level I plus 1, just as a group of gears, while a full round move of the gear triggers one move in the driven gear. For performance comparison, we have evaluated 3 key value systems, that is GearDB, LevelDB with greedy garbage collections and LevelDB with cost-benefit garbage collections, and the test environment is shown here. Same with our motivational test, we have evaluated GearDB by randomly loading 18 GB database. And the test results show that GearDB is 1.7 times faster than LevelDB in random loading. And it has a high space utilization of 19%. So we can say GearDB do achieves high performance and space efficiency. Here we show all the basic performance of three systems. From these figures, we can see that GearDB outperforms in all workloads, especially in random write. To analyze why GearDB performs better, we want to break down the random load time into different operations. Here, the test results show that GearDB eliminates on-disk garbage collections, and it also improves the compaction efficiency because the compaction time is shorter in GearDB, as we can see in this figure. Here we show the latency of each compaction during the random load process. We can see that GearDB reduces over 5,000 compactions comparing to LevelDB. So the compaction efficiency of GearDB comes from reduce the number of gear compactions. The overall compaction latency of GearDB is only 55% of LevelDB. Here we analyze the space efficiency of three systems. Figure A to D shows the space utilization of each zone after randomly loading 4 databases. There are from 20 GB to 80 GB. Figures E to H shows the corresponding CDF. First, we can see that GearDB occupies fewer zones when loading the same size database. And second, GearDB shows a bimodal zone space utilization, while most zones are nearly full and a few zones are nearly empty. Because we restrict all the fragments in the compaction windows. That's why GearDB maintains a very high space utilization consistently, that is nearly 19%. Now, I will conclude our paper. KV store on HM-SMR drive suffers from redundant cleaning processes in application level, that is compaction, and the storage level, that is garbage collection on HM-SMR drives. It results in poor performance and inefficient space utilization. And then we propose GearDB to eliminate the redundant on-disk garbage collection and improve the compaction efficiency. Through 3 techniques, new data layout, compaction window, and the gear compaction algorithm, the test results show that GearDB is 1.7 times sped up for insertion and has a high space utilization of 19%. Thank you. I'd like to take questions.
Questions?
Peter Maska from NetApp. Great work, thank you for presenting it. So some of the techniques that you are showing seems to be applicable outside of SMR drives. Like I can imagine doing the gear compaction on, for example, an SSD or just regular hard drive. Do you have any measurements or any thoughts about how much improvement you'll get versus if you use the gear-like compaction, the compaction windows on something other than SMR?
You may apply our work into different kind of hard disk, different kind of storage devices?
Right, like for example, at least I'm guessing your write amplification is a lot lower.
Yeah.
With this, so I'm guessing, so wondering if you have any measurements or any thoughts about extending to, like, let's say SSDs.
Yeah, I think SSD can apply this this policy because we manually improves the garbage collection on the log structured write. Since SSD still can also use log structured write to improve its write throughput. So I think this policy can also apply into SSD or any devices that prefers sequential write, I think.
Well, that's like most of them. So, thank you.
Thank you.
Hi, Cheng Tan from NYU. So you're talking about LevelDB, which support transaction. In your design, do you ever consider about concurrency control with your Compaction? Because concurrency control can be very fast.
What control? Excuse me.
Concurrency control. I'm meaning that transaction.
Okay. You mean when we run different multiple LevelDB on the same drive?
No, what I'm saying is like within a transaction, you touch multiple items, but it has to be atomicity, right?
Yeah.
But the question is, concurrency control can be very fast. It can be, millions of transactions per second. Like, how will that affect your Compaction?
Okay, I understand you. But in this circumstance, because we are doing this study on HM-SMR drives, so the concurrency, the improvement of concurrency on HM-SMR drives it's not like SSD. It prefers concurrency control. But in HM-SMR drives, it just has one write head. So we didn't consider that situation.
Okay, thank you.
Thank you.
This is Chen from Huawei Technologies. In my thinking, this compaction window is just a way to make sure that my question is related to if we have a skewed key range.
Mm-hmm.
Basically, you will basically push everything down from one range to another. So this is different than, let's say, LevelDB's universal compaction, which try to minimize the write unification by leaving some untouched at a lower level. So this basically what I'm trying to say. If we try to use this on SSD with multi-streams, then can you think of how this? I don't have to take the other range, which is not currently being heavily written into, so that I can reduce the write unification on those ones. I know it's different than HMR, but I think it's related.
Okay. The first thing I want to say is that actually we don't care about the key range in our study because the compaction window is composed of multiple zones. And in those zones are multiple SS tables. Those SS tables can have different key ranges. We don't really care about the key range, but we only restrict the physical space on drives. So if you comes to SSD, I think it will change the it will change the granularity of the zone into a block or something else that want sequential write. Thank you.
Damien Lemoine, Western Digital. I have two questions. So the first one is you showed the performance result using an 80 gigabyte dataset, which is about less than 500 zones of those huge HM-SMR drives, which have normally in excess of 50,000 zones. That's 2 orders of magnitude higher. So have you checked if your very good performance results maintain once you get up to that actual drive capacity? And the second question is, HM-SMR drives generally have, well, at least the models you showed on your slides, 1% capacity of it is conventional zones that can be randomly written. So you do not need anything special for maintaining, say, you don't have any constraint regarding sequential writes there. And have you looked into using that 1% space as a further optimization in your work?
Okay, for the first question, we do not do that large database test. We only restrict a small part of zones, but we do change the zone space because just as the outer checks and inside checks and outer checks by different range of checks. We tested on, we changed the checks position and to verify our design, but we do not try a very large database such as multi-terabyte. We didn't try that. So I cannot for sure that it will improve the large capacity workload. But according to our design strategy, it aims to achieve that. Okay, but and sorry for the second question, I didn't get the point.
So the HM-SMR drive, well, at least as defined by the standard, optionally can provide a small space that is conventional zones, called conventional zones, that can be randomly writable.
Yes.
The models you showed on your slides have that. 1% of their capacity at LBA0 are conventional zones. So you can randomly write those. And my question is, have you looked into using that space for further optimizing your GearDB?
Yes, thank you. Very good question. We do want to move our, yes, currently we actually do by moving the metadata from shingled magnetic zones into the conventional zone because metadata prefers random write. So we do the metadata revising on the conventional zones.
Okay, thank you.
Thank you.
Kind of a follow-up to that other question. When you restricted the capacity of the drive, did you restrict the number of zones or the size of the zones or both?
Oh, the size of zones is provided by this HM-SMR drive. It is physically fixed at 256 megabytes.
Right, so you used the whole zone. You didn't fractionally shrink it so that you would use more zones and get more of the disk activity.
We use multiple those zones.
Right. But you used a very small portion of the 50,000.
Yes.
All right, let's thank the speaker one more time.